Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're getting sketchy. That's right, we're going to talk about curve sketching. The basics that you'll encounter in the calculus class, but I'm going to introduce some techniques that allow you to get a clearer picture of what your graph will look like while doing the least intensive math necessary each step of the way, while also showing how use of a particular technique can help avoid a lot of the difficulties in quotient rules, specifically when it comes to curve sketching rational functions. There are a couple of steps in here that a lot of instructors will leave out that I'll just talk about how to do them, how to implement them, and how they can more easily give you a clear idea of what your graph should look like. So consider this scary looking function. F of x equals x squared plus 3x plus 2 over x squared minus 3x plus 2. So, basics for standard curve sketching. You need to know where the x-intercepts are and where the y-intercepts are. You need to know where any asymptotes are, horizontal, vertical, or slant asymptotes. There are no slant asymptotes here, but if there were, techniques like this would enable us to find them. Relative extrema, as well as where it's increasing and decreasing, as well as inflection points, as well as where it's concave up and concave down. So standard stuff you'd see in a calculus class. But we're actually going to get a pretty good sense of what this graph looks like without doing any calculus. So, first thing we talked about, intercepts, right? We've seen how to do intercepts before, right? You don't need to be in a calculus class to do that. Usually they'll cover that in Algebra 2 or Pre-Calc. Right? For the y-intercept, just plug in x equals 0, right? You get 2 over 2. No huge mystery there. And if that is a mystery to you, then you probably won't understand the rest of what goes on in this video. For x-intercepts are where the y value equals 0. So you can factor this numerator and this denominator, right? X plus 1 times x plus 2, x minus 1, x minus 2. Shows us that when x is negative 1 or negative 2, numerator goes to 0, so that's where the x-intercepts are going to be. Denominator is going to be factored into x minus 1 and x minus 2, so if x is 1 or x is 2, then you try to divide by 0. That never quite works out the way you planned it. And so that means that you're going to have a vertical asymptote. So vertical asymptotes at x equals 1 and x equals 2. X-intercepts at negative 1 and negative 2. Note that does not mean horizontal asymptotes of negative 1 and negative 2. For the horizontal asymptotes, you say, well, if x is really, really big and positive, what's this doing? And, it's going to go to 1, right? The x squared dominates, right? So you either cover that in pre-calc or possibly like the very, very, very beginning of calc when you're just doing limits. And then also if x is large and negative, right? It's also going to go to 1, right? And you can imagine, if x is like 1,000,000, then you've got 1,000,000 squared plus a couple more millions divided by 1,000,000 squared, right? It's the squares that are going to dominate, right? So for large positive x, it goes to 1. For large negative x, it also goes to 1. Yeah. So we get that there's a horizontal asymptote at y equals 1, and that the graph approaches that asymptote at both ends. Yeah. So, our graph thus far looks like this. Horizontal asymptote, vertical asymptotes, y-intercept here. Notice that the y-intercept happens to be perfectly on the asymptote, but that's just an anomaly of the function I chose. And we've got these x-intercepts here. Okay. Not too clear a picture yet. What else can we do? Let's try to find behavior near the asymptotes. And this is the first step that a lot of instructors skip over. So we know that at x equals 1, there's an asymptote. What if x is a little bit less than 1? Well, then these two terms in the numerator are both positive. If I've got a little bit less than 1 minus 2, that's going to be negative. And so the sign of this function entirely depends on the sign of this x minus 1, right? If x is a little less than 1, then this is negative. I have two positives divided by the product of two negatives. That's going to be positive. So if x is a little less than 1, I know this is going to be a positive number. And because I have a tiny little decimal in the denominator, I know it's going to be large and positive. And the opposite if x is a little bit more than 1, right? That would make this x minus 1 like 0.01 instead of negative 0.01. I'll still have two positives in the numerator, and my denominator, my 0.01, will still be multiplied by a negative. So I'll have a large negative if x is a little bit more than 1. And the opposite happens if x is a little bit less than 2 or a little bit more than 2. It's negative from the left and positive from the right. As you can see, these will still be positive in the numerator. Now this x minus 2 is the one that's going to switch sign, depending on if you're a little below or a little above. And if x is around 2 minus 1 is around 1, that's positive. Right? So now it's negative from the left and positive from the right. So that's the behavior near the vertical asymptotes. And later on I'll show another way of determining what the behavior near the vertical asymptote should be like. So now our graph thus far looks like this. All I've added here, we know that it's positive to the left of the asymptote, negative to the right, and then here, negative to the left, positive to the right. But that gives us a sense of what we think this is going to do. We think we know how it's approaching the asymptotes. And this guess will end up being correct, but we'll do some more work to formalize it. But already, without doing a whole lot of work, we have a pretty good sense of what this is supposed to look like. So, to find the end behavior, for x being large and positive or large and negative, we'll use long division of polynomials. And this long division of polynomials will end up being useful later. We do our long division, right? X squared goes into x squared once. We subtract off this x squared minus 3x plus 2. We get our remainder, right? 6x is lower order than x squared minus 3x plus 2. So we get that our function is 1 plus 6x over x squared minus 3x plus 2. And pretty clearly, if x is, say, around 1 million, then this numerator will be like 6 million-ish. This denominator will be like 1 trillion-ish. So pretty clearly, this f of x is going to go to 1. And if x is like negative 1 million, then we've got, negative millions in the numerator, trillions in the denominator, still going to 1. So we've got this horizontal asymptote, and the function approaches that asymptote at both ends. But now, to figure out how it behaves near that asymptote, if x is large and positive, let's look more closely. We said this is like 6 million over 1 trillion. That's a positive tiny little fraction. So for large x, this approaches the asymptote from the top. And for large negative x, this approaches from below. It ends up crossing the asymptote when the numerator is 0, right? Which happens to be x equals 0, which we already happened to know about. But it is nice to know where it crosses the asymptote. And if there were other points where it crossed the asymptote, we want to know about that. Right? We happen to know this, know that it crossed the asymptote there already because it happened to be the y-intercept. That was pure coincidence. If we didn't know that then, we would have known that now. When we checked when does this thing we're adding to the constant 1, when does that go to 0? It goes to 0 when 6x goes to 0, which happens when x is 0. So, our graph thus far, we now can fill in this and this as blue, right? We know for sure that it's going to be approaching from the bottom for large negative x, and from the top for large positive x. There's one last step to make the calculus easier, right? Because if you look at this function here, if we wanted to find the first and second derivatives for finding critical points and points of inflection, right, we look at this And we get all queasy because we don't want to quotient rule this, especially not twice. But if we use partial fraction decomposition, because this is a rational function, we can do that. Assuming you remember how partial fraction decomposition works, a over x minus 2 plus b over x minus 1. Remember, these are the factors of the denominator. Cross multiply, set it equal to this. You can either solve your system of two equations and two unknowns, or plug in the values of x that will make these go to 0. Either way, we get a is 12 and b is negative 6. This isn't a video about partial fraction decomposition, so that's all the detail I'll go into on that. If you're a little confused about this procedure, you're already on YouTube, pause the video, go into the search bar, type in partial fraction decomposition, and someone should be able to explain that more clearly than I just did. But now we have a nicer looking function, f of x, right? Same f of x, it's just written in a nicer form. And now if we think about differentiating this, we don't actually need to do quotient rule, right? We can think of this as 12 times x minus 2 to the negative 1 and 6 times x minus 1 to the negative 1. And that's much nicer to differentiate twice. And so we'll do it that way. But before I do that, I will point out this one other thing. Looking at this function here, we have it's 1 plus a positive number over x minus 2 and a negative number over x minus 1. Now remember what 1 over x looks like. It has that vertical asymptote where it's positive on the right, negative on the left. And so, because we have a positive here, that means it really is going to be positive to the right of x equals 2 and negative to the left. And because we have a negative here, it's going to be positive to the left, negative to the right. Exactly what we saw over here. And apparently my cat wants to say hi. You want to say hi to YouTube? My pride and joy. So, now that we have this version of f of x, we can differentiate once. Get this expression here. Algebra happens. We move this to the other side. Multiply by x minus 2 squared, divide by 6, take the square root of both sides. Do some more algebra, and we'll get these two values of x. These are going to be the potential critical points. Now normally you would say, well, we need to test to see if these really are critical points. But take a look at these numbers here. Negative 1 point something, positive 1 point something, right? If we rationalize the denominator, we'd actually get that they're exactly negative root 2 and positive root 2. But take a look at the graph over here. Negative root 2 would put you somewhere between these x-intercepts. By Rolle's theorem, there has to be a point in between where you get a horizontal tangent, and if we only find one such point, we will know with certainty that it's a critical point. And if we only find one such point over this whole region of the graph, we'll know it has to be a minimum, because we know the graph was increasing over here. That's the only way it could get from 0 to 1. And here it went from 0 to almost 1. Or I guess going the opposite way, from almost 1 to 0. So because it went from decreasing to then increasing again, we know this has to be a critical point. We can state that with certainty without doing first or second derivative test and without number lining and figuring out where, without plugging into the derivative and seeing if it's positive or negative. Just from our sketch of the graph, we were able to suspect that there was a turning point here. And now we can confirm it saying the value is negative root 2, And there's no way that we can avoid any critical points here, right? You can't go from heading down to heading up without turning around, and there's only one point where you could turn around. Meanwhile, take a look at positive root 2. That's between the asymptotes. Now we know that our graph was coming up from negative infinity and then headed back down to negative infinity. You can't do that without turning around. So we know there's got to be a critical point somewhere in here. And when we find only one potential critical point, that means we know with certainty that it is a critical point without needing to do first derivative test or number line. And if we think a little ahead to points of inflection, we would suspect that our graph is concave up here the whole time, and concave down here the whole time, and concave up over here, and turns to concave down here. Now, we know it's concave up at least somewhere here, right? You can't go from decreasing at a negative infinite slope, right? That's the only way you can come from negative infinity like that. Slope has to be negative infinite here. And slope has to be 0 here. So we know that it's concave up at least over some portion here. We suspect it's going to be doing that for the whole time. And we know that it's going to be concave down for at least some portion here. We suspect it'll be doing that for the whole time. And we know that this function is concave up for at least some portion here. But we also know it's got to be concave down over here. How do we know that? Our slope had to be about 0 at the asymptote, right? That's how you can approach an asymptote. Slope 0. If you zoom right past it with a non-zero slope, that's not an asymptote. And we know we were actually decreasing in between, so we went from 0 slope to negative slope. And then we went back to 0 slope. So we know there has to be a point of inflection somewhere here. And if we only find one potential point of inflection, then we will know with certainty that it is a point of inflection. So, let's find the inflection point. And this is the part that I suspect would be incredibly challenging to do without the partial fraction decomposition trick. Just because it involves a cube root. I was going to go through all the algebra. In preparation for this video, I got up to this point of the algebra, looked at it and said, I'm not doing that. If you'd like to try it, you are braver than I am. Power to you if you can actually pull it off. But this is the way I would find the inflection point. Looking back at the f prime of x we had right up here, we just take one more derivative, right? So again, when it's in this form, that's not hard to do. And doing that same trick as we did before, of moving the negative to the other side, doing our multiplication by x minus 2 cubed, division by 12. Right, we get x minus 2 cubed over x minus 1 cubed, which is x minus 2 over x minus 1 quantity cubed. Right, we get that's equal to 2. X minus 2 over x minus 1 is cube root of 2, which is 1.26. Algebra happens. Right, so this 1.26 is obviously a rounded figure. You could keep it a little more precise if you wanted to, but I want to have it in decimal notation so that we can actually, put it on the graph. We get that x is around negative 2.85. So we get a potential point of inflection at negative 2.85 and no other potential points of inflection. And, if you remember, we said there had to be a point of inflection to the left of our critical point. Because we know it went from going down to curving back up. So I guess I should move from left to right. We know that it went from slope of around 0 to negative to 0 again. It can't do that without switching concavity. Slope is decreasing from 0 to a negative, and then increasing back to 0, and then continues to increase. And then it has a discontinuity here, and then goes concave down, then has a discontinuity here and goes concave up. But we'll see, we notice that everything here, the only stuff we've really added is stating with certainty where the critical points of the inflection point are. And we could find out most of that information, or at least suspect most of that, using earlier techniques and without using heavy calculus. I hope you found this useful, and as always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. And until next time, this is Dr. Nighttime wishing you a good night.